Okay, I'm going to be giving 2 lectures.
One more thing. This evening at 7 o'clock, there will also going to be participant talks.
So I'm going to be giving 2 lectures describing work by Beasley, Heckman, and Vafa on gut-like models via F-theory. I got to tell you that the 2 papers are a total of 300 pages long, and I've tried to study them so I can give you these lectures. I might be somewhat short of an expert, so there might be points where you can help out. But on the bright side, I'll try to make it a little bit easier to understand than it is in those papers, which will be good for the lectures, but it has the slight drawback that if you decide to read the papers, you will have to get used to the language that they use a little bit better than I will be able to explain it in 2 lectures. Now, the goal is that they're going to do an SU5-like model. They discuss lots of things in the 300 pages. I'm going to try to make a straight route to the part of it that I find most interesting. They make an SU5-like models by F-theory, which I understand Herman has told you something about, on a vanishing cycle. A vanishing cycle just means that in a larger manifold, there's a small piece that's shrinking. So W, or actually in the lecture I think I'll be calling it S. S is a 4 manifold. And all our fun is going to happen near a 4-dimensional subspace of a bigger 6 manifold. And it's a small 4-dimensional subspace, so there's a little corner where all the fun will happen. So we're going to have a local gut-like model. Local means that the details of what B looks like away from the vanishing cycle won't matter. All the fun is going to be near that vanishing cycle. Now, in the literature, there are lots and lots of papers where people construct standard model-like models. From a bottom-up approach, they're local. Maybe there's some intersecting D-branes, for example. That's a very popular approach. Most models that give local constructions of something similar to the standard model don't incorporate the successes of grand unification, especially with the value of sine squared theta in the weak interactions. What I think is unusual, and it's really the reason I'm giving the lectures, I think. What makes this unusual is that it's a local model that I'm not sure if I should say predicts, incorporates, or describes, but it incorporates the gut prediction for sine squared theta. After all, the gut prediction for sine squared theta is, well, one of the nicest insights we have about physics way beyond the standard model. And to me, it's the most convincing reason to suspect that low-energy supersymmetry might be relevant. So typically, it's a shame that typically, on the other hand, it's a very attractive idea that maybe observed particle physics somehow is supported locally in the 6-dimensional manifold and doesn't depend on all the big picture details. It's a shame that usually when people construct the standard model at some kind of intersection or some kind of local phenomenon, the price of admission is that one abandons the gut prediction for sine squared theta and possibly the gut explanation for the quantum numbers of the quarks and leptons. So what I think is really unusual about this model is that it's a local model that incorporates the successes of guts. That's why as I say, that's why I'm giving lectures about it. The other thing is that it gives nice answers to questions that, since early days of work on the perturbative heterotic string, seemed like they should work, but are actually troublesome. You can make them work, and you've heard some approaches by starting with Robbie's lecture and others here, but there are a variety of problems that you'd think you could treat in the perturbative or even maybe strongly coupled heterotic string, but turn out to be tougher than they look. And these include doublets, triplet splitting, and avoiding rapid proton decay, which could occur via terms in the superpotential, either 5 bar 10, or 5 bar 10 cubed. We could have either dimension, 3 or 4 terms in the superpotential corresponding to dimension 4 or 5 interactions in the ordinary Lagrangian, which would either cause the proton to decay like a kaon or something like that, or that's what the first one would do, or the second one would make the proton decay slowly by elementary particle standards, but still way too fast. So I think that they have interesting perspectives on these problems as well. And I'll hope to get into that tomorrow. Now, the first thing to say is that F-theory is not exotic. It's really just type 2b, in a sense. So type 2b has 2 scalar fields, or 2 spin 0 fields, a scalar and a pseudoscalar, that can be conveniently combined to a complex field, I over G string plus A over 2 pi, where as usual G string is the exponential of the dilaton. And tau is a complex number in the upper half plane. Type 2b has S duality. That maps tau to A tau plus B over C tau plus D, where A, D, B, and C are integers, and they correspond to a 2 by 2 matrix of determinant 1. Now, supersymmetry, when we compactify, supersymmetry doesn't force tau to be constant. We reduce the supersymmetry if tau isn't constant, but as long as tau is holomorphic, we still have a supersymmetric situation. Let's do type 2b on a Calabi-Yau. I'll call the Calabi-Yau x. So we're in Minkowski space R13 times x. Well, that gives n equals 2 supersymmetry. N equals 2 is more than we want for describing particle physics. We'd like to get down to n equals 1 anyway. When we compactify on a Calabi-Yau, Calabi-Yau means that tau is constant. So supersymmetric compactification of type 2 with constant tau and no fluxes or branes gives n equals 2 supersymmetry, which is not exactly what we want. If tau is not constant but is holomorphic, that leaves half the supersymmetry, which would be n equals 1. So tau is holomorphic but not constant. That gives n equals 1 supersymmetry, which is actually what we want for particle physics in 4 dimensions, or what we might want for particle physics 4 dimensions at TeV energies. Now, there is a technicality that in this case, X should not be Calabi-Yau, but has positive Ricci curvature. Calabi-Yau means Kähler and Ricci flat. Ricci equals 0. When tau is not constant, of course, the derivatives of tau, the stress tensor of tau contributes to the Einstein equations. So when you obey the Einstein equations, there's a source term due to tau, as a result of which X should not be Ricci flat anymore, but needs positive Ricci curvature. So many of the ideas are the same, but X is not Calabi-Yau. X is still Kähler. That means a complex manifold in particular, but more specifically a Kähler manifold. But it's a different Kähler manifold. It's one of positive Ricci curvature rather than Ricci curvature 0. It's actually better in the following sense. Calabi-Yau threefolds are very numerous and they're not classified. There are tens of thousands of them. But the kind of positive Ricci curvature Kähler threefold that you want here, they actually are classified and they're more limited in number. So when we make tau non-constant, we can use some similar ideas in compactification. We still use Kähler manifolds. We still compactify on a type 2b on a 3-dimensional complex manifold. 4 in a sense that we'll get to later on and that you've probably heard from Herman. But it's got the advantage that the choices are a little bit more constrained. Probably, when all is said and done, we get the same very large number of vacua. But at least at the starting point of saying what manifold we're using, it's more simple. Now, since I should give some explanation of the fact that we can preserve supersymmetry while tau not being constant, I'm going to give some very elementary examples. The most basic example is a D7 brane. So we take a D7 brane, well, we're in 10 dimensions, let's say, but we factor it as R17 times R2. This is supposed to be the world volume of the D7 brane. I'll just draw the transverse R2, which we'll think of as the complex Z-plane. And we put a D7 brane at the origin. Well, if you want to know what tau is near a D7 brane, you find out by solving the equations of supergravity. And the supergravity solution tells us that tau is minus I log of z over z0 for some z0. So this is the solution, plus regular stuff. This is a solution for z near 0. So the 7 brane is at z equals 0. So I've written down the solution that's good near z equals 0, near the D7 brane. You might notice, actually, that tau is supposed to be in the upper half plane, which it is if z is near 0, but if we let z become very large, the imaginary part of tau would become negative. So something is wrong with that solution very far away from the D7 brane. It's a phenomenon that's a little bit analogous to confinement. Since the D7 brane only has 2 transverse directions, it's too big a source in the Einstein equations. So D7 branes are confined. So you can't have a D7 brane all by itself in infinite space. The solution behaves badly at large distances. If Z0 is very large, then Z has to be very large before you run into trouble. But any solution involving a D7 brane needs to somehow be fixed at infinity. But we're not worried about that right now. It makes perfect sense near the D7 brane. whatever else there is outside doesn't affect the solution near z equals 0, and this is the right solution near z equals 0. Now, I don't want to solve Einstein's equations for you on the blackboard, and I also don't want to assume that you remember this solution. So I wanted to explain why it looks like this. The reason it looks like this is that there's a monodromy under z going to z plus 2 pi I. Sorry. I should say under log z going to log z plus 2 pi I. In other words, under monodromy around the z-plane, tau goes to tau plus 2 pi, which means that, gosh, I've erased the definition of tau, which was I over g string plus a over 2 pi. I guess I want to 1 over 2 pi here. So a goes to a plus 2 pi. So the meaning of the logarithm is that the axion-like field A has a monodromy in going around the 7 brane. Now, that's equivalent to something that you actually know about. The basic claim to fame of D-branes in general is that a D-brane is a source of Ramond-Ramond flux. What that means is that if we draw a sphere around the D-brane and integrate the appropriate Ramond-Ramond P form, we get 1, the D-brane charge. Well, for the case of a D7 brane, a sphere around the D7 brane is that circle. So we're supposed to integrate over that circle g1 over 2 pi, and that should be the D-brane charge, which is 1. So a D7 brane should have the property that the Ramond-Ramond 1 form integrated over that circle is 2 pi. But G1 is dA. The Ramond-Ramond 0 form field is the potential for the Ramond-Ramond 1 form field strength. So in other words, the fact that the D7 brane carries D-brane charge tells us that the integral of dA over 2 pi over this S is 1, or in other words, it tells us that A has this monodromy around the D7 brane. Well, if A is supposed to have that monodromy, but also supersymmetry makes tau holomorphic, then tau has got to look like this. In other words, what this logarithm is a holomorphic function that has the right monodromy. Well, here's another example, but it's going to be rather painless. We're going to do n D7 branes. In that case, the Ramond-Ramond charge is n. So the monodromy has got to involve a 2 pi n. And therefore, tau has got to have an n in it in front of the logarithm. So this is another example of F-theory. A supersymmetric configuration where tau is not constant is what we mean by F-theory. There are fancy methods to study such things, which we'll even introduce eventually. But the basic idea is just a supersymmetric configuration where tau is not constant. Well, there is one more elementary example. Which is that we could add an O7 plane. Well, we could combine it with this, but first we could have an O7 plane. Well, I think I will combine it right away. I add an O7 plane plus, well, n full D7 branes, which is the same as 2n D7 branes on the covering space. The O7 plane means we divide by z z going to minus z. So in general, an orientable plane means that we divide the normal space by z2, a sign change on all coordinates. Here, the normal space is just the complex z-plane, so the orientifolding is z going to minus z. That gives a supersymmetric configuration. It actually carries, if we don't have any d7 branes, it carries a Ramon-Ramon charge, which is negative. So because there's a negative Ramon-Ramon charge, the solution just with the d7 brane is like this, but n is a negative integer. I'm afraid I got confused last night about whether it was -4 or -2. If anyone wants to comment, please do. But what? Well, I know it should be -4, but there's something that we'll get to eventually that came out better if I used -2. I might not get to it until tomorrow, or maybe this afternoon session. Okay. All right, so with 2n d7 branes, then the charge, John tells us, is -4. I can even tell you why that's the right answer. It's just that I did run into a snag. The usual way it's said is that an O9 plane has orientable charge -16, which is why the gauge symmetry for type 1 is SO32, 32 being twice 16. But then when we compactify on a 2 torus and totalize, the O9 plane splits up into 4 O7 planes, so they each have charge -4. So that's an extremely convincing argument, but I did need -2 for something else, and I didn't quite figure out the snag. Okay. But hopefully you'll still be here later on, so maybe you'll be able to fix it. So I've given sort of 2 examples of F theory, and an interesting fact is that they involve gauge symmetry. So n d7 branes, the gauge group is UN, and an O7 plane with n full d7 branes, the gauge group is SO2n. And these are perfectly good gut groups, sort of. 2 of the most famous gut groups are SU5 and SO10, which are almost examples of this. Here we get an extra U1, but actually in string theory there are lots of mechanisms where U1s disappear by being anomalous and get eaten up and become massive. So although the local computation here gives U5 if n is 5, it's quite possible that when all is said and done, the gauge group will really be SU5. So I've given you 2 examples of F theory that we didn't need F theory for. We just drew simple elementary D-brane configurations, or maybe with an orientifold plane, and we got 2 of the most important gut groups. Of course, we didn't get E6 that way, but okay, SU5 and O10 or SO10 are pretty good. So you could ask, and this is a very basic question, since D-branes and O-planes are more elementary, could we make a model just using D-branes and O-planes without learning F theory systematically? Do we need F theory? And the answer is that we almost don't need F theory beyond this kind of elementary. Okay. This type of configuration can be interpreted in terms of F theory, but okay. You might have felt you were happy with D7 branes without being told some of the things I just told you. So could we redo the Vafa-Beasley-Ekman papers without really having to learn F theory? Well, the answer, as they explain, is almost. So we can understand a lot of the stuff without F theory, but eventually it'll turn out that it's better to incorporate the F theory language. But let's see how far we can get without F theory. Any quick questions from what I've said so far? Yes?
So this is all just done in 2D, but I guess when people talk about F theory, they sometimes talk about 12 dimensions. Can I see that in this?
Well, if you describe this in a more sophisticated way, it's convenient to introduce 2 more dimensions. You add an elliptic curve whose tau parameter is tau. But it'll be a while before I say anything where that's useful. And I didn't want to add that extra level of abstraction right now. Any other questions? So, as I say, we're going to try to describe the model without F theory. But like I told you, what the model is it's a model in which we compactify type 2b on a 6 manifold that we called B with variable tau. But there's going to be a 4 manifold in B where all the fun is happening. And we want to have a gut group on that 4 manifold, and the gut group is going to be SU5. We could have started with SO10, but then we would need F theory faster. If we aim for an SU5 model, we can get farther without F theory. So I'm just going to draw the 4 manifold. And we add to it, I'll call it S. And we add 5 D7 branes wrapped on S. So we've got U5 gauge symmetry. And, well, first of all, the extra U1 might not be harmful for particle physics, but in case it is, as I've told you already, extra U1s often disappear when you describe a global construction. Locally, it will look like U5, but when you embed it in B, very often, somehow, the extra U1 will get eaten up. So we got the gut gauge group in a local construction. So are we happy? Well, not quite. At a minimum, we need 5s or 5 bars of SU5. Well, we need 5 bars for quarks and leptons. I'm describing chiral superfields, right? Left-handed chiral superfields. So the electron neutrino doublet and the down quarks, I guess, well, down antiquarks, are in the 5 bar. So we need at least to get 5 bars. But really, to get Higgs bosons, we need 5 plus 5 bars of SU5. So we can't rest just with D7 branes that give us SU5 gauge symmetry. We need a way to get 5 plus 5 bars. Well, if you've studied your D branes, you know how to get a fundamental representation of the gauge group. You just intersect your D brane with another D brane. So here's a new picture. In addition to S, so there are 5 D7s here. We're going to have another 4 manifold, which intersects S in what I'll call C. And this has 1 D7 brane. Well, in 6 dimensions, 2 4 manifolds will meet on a 2 manifold generically. And that's very important in this, that S, which intersects what I'll maybe call T is the world volume of the other D7 brane. S intersects T on a Riemann surface. S intersected with T is a 2 manifold that I'll call C. Okay. We're going to run into a case where simple dimension counting is wrong, but this isn't such a case. It's natural in 6 dimensions that 2 4 manifolds would have 2 dimensions in common. And so generically, S intersects T in a Riemann surface. Now, on C, so all this is, of course, multiplied by R13. So this is the intersection. And the brane intersection contains a 5 plus 5 bar of SU5. Actually, it's even U5. It's a 5 plus 5 bar of U5 in 6 dimensions. And of course, we're interested in getting down to 4 dimensions. To get down to 4 dimensions, we need to solve the Dirac equation along C. And the Dirac equation along C will depend on gauge field fluxes that we might turn on. For example, we will eventually do something more complicated for reasons I'll explain. But the simplest thing we could imagine doing is to turn on a U1 gauge field, either the one on T or else the center of U5. Okay, if we don't turn on anything, we'll solve the Dirac equation on C and it will have no zero modes. So we'll get no massless 5s or 5 bars in 4 dimensions. But if we turn on k units of flux, we'll get k 5s or minus k 5 bars, depending on whether k is positive or negative. So a single smooth brane intersection can give us any number of 5s or 5 bars, depending on the magnetic flux. If you want 5s and 5 bars, you could have a T and also another T prime. One has positive flux, one has negative flux. Then you'll get 5s on C and 5 bars on C prime. I shouldn't state that hypothetically because we will want to do that eventually to get Higgs bosons as well as standard model 5 bars. Actually, eventually we're going to need 3 of these. One for the Higgs 5, one for the Higgs 5 bar, and a third one for the 5 bars that contain quarks and leptons. Now, we learned from this simple example a very fundamental fact in the picture of Beasley, Ekman, and Vafa, which is that gauge theory is supported on the 4 manifold S, but matter is supported on a 2 manifold inside S. And so we got 5s and 5 bars, and that wasn't even too hard. But the SUSY GOTs also have 10s, so we need to get 10s. We need a way to get a 10. But again, if you know your branes, you might realize how to get a 10. We can get, before drawing a picture here, I'm going to just draw a little bit in isolation. Here we have n, 5 d7s. And now we let them intersect an orientifold plane. Well, in the presence of an orientifold plane, everything has to be mirror symmetric. So there's a mirror of these 5s. Okay. I think I've called this S. So there's a mirror of S, which I hope I can draw. Trouble is I don't know how to draw it. Okay. I'll try to draw it in a different color. Okay. That's meant to be the mirror, S prime. So it has 5 more d7s. And then, to quantize this mess, you can first ignore the orientifold plane and calculate the spectrum, and then you have to make an orientifold projection. So, in particular, you have the S prime strings. They're bifundamentals of U5 times U5 before the projection. After the orientifold projection, we get 10s of U5. The orientifold projection breaks U5 times U5 to the diagonal U5. Before the projection, S and S prime each had 5 d7 branes, and each had its own U5 gauge symmetry. But when you do the orientifolding, you identify one with the other. So you consider those two U5s equivalent, and you only keep the diagonal U5. And similarly, you project out half of the matter fields, which previously were bifundamentals. Okay, whether you keep a 10 or a 15 of SU5 depends on which Orientable projection you're making. But we're doing the Orientable projection of orthogonal type. It's the one related to F-theory in a more simple way. And in that case, you keep the tan of U5. I hope, by the way, you all know what the tan is. The tan is the second-rank anti-symmetric tensor. You should know that if you've studied GOTs even a little bit. Because more or less the first GOT group is SU5, and the representations 5 bar and 10, what they are, is practically the first thing you'd learn about the SU5 model. Okay. So that's the strategy for getting. That's a strategy for getting a 10. This is, of course, a 6-dimensional 10. In other words, a 6-dimensional hypermultiplet. Hypermultiplets are really pseudo-real representations. So when I say 10, it's a shorthand for 10 plus 10 bar. Just like when we got a 5 from brane intersections. In 6 dimensions, it was 5 plus 5 bar. So anyway, this gives the prototype for how we're supposed to get 10s. What we did here was we simply intersected our D7 brane with an Orientable plane. We got 5s by intersecting the D7 brane with another D7 brane, and we get 10s by intersecting it with the Orientable plane. So I'm going to draw a picture for that. The picture will look the same, almost. Well, so here's S. And, I don't want to, I'm going to draw a dotted line for the Orientable. So the picture is exactly the same picture. Too many dotted lines. It's the same picture, except that while I represented T by a solid line, I draw the same thing, I maybe call it U, for the Orientable plane. So this is an 07 plane. And the 07 plane also meets S in codimension 2, so it also meets S on a Riemann surface that I've called D. U intersect S is a 2-manifold, another 2-manifold D. Now, because of this exercise I explained over here, we have 10 plus 10 bar on D. Now, I haven't drawn everything in this picture because it would be too busy. To explain why we got the 10 over here, we had the 07 plane intersecting S, but S wasn't invariant under the Orientable projection. So there was also an S prime, a mirror of S. The 07 plane was coming in at an angle, so that if we make the Orientable reflection with respect to this axis, S is mapped to something else. So the idea is the same here, but I haven't tried to draw everything. The 07 plane is coming in at an angle. S isn't invariant under the Orientable projection. It has a mirror image that's somewhere else. There's some place where all three of them intersect, like in this picture. And the same discussion shows that there's a 10 plus 10 bar at the intersection. Over here, I've drawn the intersection, which corresponds, in this picture, it just corresponds to that point. Because here I've drawn a slice through this picture, which is trying to be 4-dimensional. But the more complete version of this picture here would have shown S prime. And that would account for how we get the 10 plus 10 bar. Okay. Well, it's the same story that I just told you. We get a 6-dimensional 10 plus 10 bar. But to get 4-dimensional 10s or 10 bars, we need to solve an index problem. We need to solve the Dirac equation along D, and that will depend upon the U1 flux. And if we want 3 generations, we take the U1 flux to be 3, and we get 3 10s in 4 dimensions. And no 10 bars. So we've more or less gotten the particles of SU5 gut. But we're not done because we also need Ukala couplings. Right? A very important part of SU5 gut is to give Ukala couplings. Well, now, we're going to have to combine the two pictures to get any Ukala couplings, because Ukala couplings combine 5s and 10s. The renormalizable Ukala couplings of SUSY guts are 5 bar 10 10 and 5 bar 10 and 5 10 10. So there aren't any renormalizable Ukala couplings that only involve 5s or only involve 10s. So therefore, a Ukala coupling involves both a 5 and a 10, roughly speaking, at the crude level of not distinguishing 5 and 5 bar. And therefore, to get anywhere, we're going to need to draw a picture that combines this picture and this one. So let's combine them. I've luckily got it drawn here, so I can copy it. So this is S, and there's a T, and T comes in and meets S on a Riemann surface C, and that's why we have 5s. Now, it's a fundamental fact of life that in 4 dimensions it's natural for two manifolds to meet each other. Just like two lines can meet each other in a plane, because 1 plus 1 is 2. The important one is not the dimension of the line, but the dimension of the normal space. So it's one condition to be on a line and one condition to be on another line. And in 2 dimensions, you can obey 2 equations. So lines meet. Similarly, two-dimensional planes meet in 4 dimensions generically. And if they do meet after any small perturbation, they keep meeting. So it's reasonable for C and D to meet. It doesn't involve any fine-tuning. The fancy way to say it is that they have a non-zero intersection number. So I'll just draw a generic picture where C and D intersect at a point. So there are 5s or 5 bars on C, depending on the flux, and there are, let's say, 10s on D, depending on the flux. And there's a point where C meets D. Now, I'm going to draw, I don't want to draw, it's important to draw mirror images, but if I put the mirror images on this picture, it would become too busy. So I'm instead going to draw a picture like this one, showing both S and T. So I'll draw a 2-dimensional slice through there. So there is an orientable plane. That's one part of it. That's U. And then there's the region where we're building our gut. That's S. But S is meeting T. And when you draw it in a plane, it seems funny that 3 lines meet. But in 6 dimensions, it was perfectly natural. All 3 of these are of codimension 2, and 3 codimension 2 objects should meet at a point. That's completely natural in 6 dimensions. But I may have picked unlucky angles here, but okay. I've drawn T and S coming in not perpendicular to U, but at some random angle, and they've got mirror images. So now I'm going to draw the mirror images. So T prime is the mirror image of T, I hope. And then S has a mirror image too, S prime. So now a lot of lines are meeting, but it's actually still natural, because given that S, T, and U met at a point, S prime and T prime are stuck meeting at the same points. And up in 6 dimensions, it was completely clear that there's a point where all 3 of these 4 manifolds meet. That's generic. So what we've got here is still generic, even though as a 2-dimensional projection, it might raise some questions. Now, you see, well, forget the orientable plane for a moment and just look at the fact that there are 4 different D7 branes all meeting at a point. They are S, S prime, T, and T prime. That enables us to draw a perturbative string diagram. Where I put S here, S prime here, and T here. I could also make an orientifold projection. I could exchange all the primed and unprimed objects, and it would be equivalent by the orientifolding. That would exchange S and S prime, but we have both of them, so that wouldn't matter. We just flip the picture over and map them back, and it would turn T into T prime. So fundamentally, what I've done here is I've put S in its mirror image. S is singled out because that's where we're doing gut physics. And I put either T or T prime for the third one. It didn't matter which because of really orientifolding. Now, in the S prime channel, we get a 10. And in these channels, we have 5s or 5 bars, potentially. But group theory only allows us to have a non-trivial coupling if they are 5 bars. So in other words, in 6 dimensions, there were both 5s and 5 bars there. But when you work out this string diagram, you're going to get the coupling of 2 5 bars to a 10. If I haven't confused you, then you understand that this is a string diagram you can completely explicitly work out. You can take everything to happen in R6. No need. We're only interested in the local behavior near where everything meets. And the manifold might as well be flat, so it could all be in R6. And S, T, and U could all be flat. So these are D branes and O7 planes that you can describe by free 2-dimensional field theory. And this string diagram is a standard coupling of 3 open strings. And it manifestly is U5 invariant, with U5 being carried by the Chan-Paton factors. So we get a Ukala coupling, 10, 5 bar, 5 bar. Any questions there?
Do you generate higher dimensional effective operators too?
Of course. But the 10, 5 bar, 5 bar is the most important, the most immediate one we generate. And I stressed it because we need it to give down quark masses, as well as charged lepton masses. So we're happy because we can give the down quark and the electron masses. And we're potentially in a panic because the proton might decay rapidly. We might have produced a proton lifetime much less than a nanosecond if we have the wrong 10s and 5 bars coupled in there. So this is a double-edged sword, but that's inevitable in grand unification. But we haven't gotten masses to the up quarks. I'm not sure what I can erase. Okay, let's erase this. Up quark masses come from 5, 10, 10 couplings in SUSY guts. But we've got a problem because the up quark masses are not U5 invariant, only SU5. And the D brane construction really produced U5. So we have to get rid of the U1. And as I told you, there are a lot of ways to get rid of the U1. So first of all, if we don't get rid of the U1, the up-quark masses will be exactly 0. So as we'll discuss in a moment, even if we get rid of the U1, the up-quark masses might be too small. But let's first try to keep them from being exactly 0. Well, I'm just going to give you 2 examples of ways that the U1 could disappear. I don't think it's a complete list, but one thing to remember is that there's an NSB field. And on the world sheet of a brane, for example, one of them has world sheet R13 times S. There's a coupling, the integral over W, of B minus F U1 squared. In other words, the usual Maxwell coupling would be F squared. But for the U1, F squared isn't gauge invariant. It mixes with B, the Navier-Schwarz 2 form. So the correct coupling is B minus F U1 squared. And there's a good chance that that will gauge away one of the U1s. Now, only one, because there's only one Navier-Schwarz B field. And there are potentially a lot of world volumes of D7 branes. But anyway, this is a good strategy for getting rid of one U1. It'll be gauged away mixing with the Navier-Schwarz B field. Okay, that's one thing. Another thing is that we use the Ramond-Ramond 4 form potential, which I'll call C4. The Ramond-Ramond field strength is dC4, and that's the fellow which is self-dual. So any statement about C4 is tricky to formulate exactly right because of the self-duality of G5. But we won't need to worry about any subtleties. We'll just say something simple, which we don't quite have room to write without removing this nice picture, but I'll try. There's a coupling C4 wedge F U1 wedge F U1 integrated over W. And now, in this construction, we needed to give vebs to the U1Fs because otherwise our index theory would be trivial and we wouldn't have gotten any 4-dimensional massless chiral superfields. So F will have a vev, for some of the Fs at least, on some of the branes. And then when that happens, potentially, a mode of C can mix with one of the Fs to make a massive field. Yes?
What if we got rid of this one and tried to get rid of even 1 to the 5 and 2 to the 10?
Yes. Well, it only became anomalous when we turned on a flux. Because we didn't, oh, we mean in 6 dimensions, sorry. What? But we only get, well, remember to get massless superfields in 4 dimensions happens if we turn on U1 fields, because otherwise the Dirac index theory gives 0. So to get a 4-dimensional anomaly, we've turned on FU1, so I think maybe it's this second mechanism, perhaps. When we turn on it, when we give a vev to the U1, one of the U1 field strengths, there's a good chance of it getting Higgsed away because of this term. And we have to give vevs to some U1s in order to get chiral superfields in 4 dimensions. So I'm being a little bit vague because I haven't told you exactly which U1s we're going to turn on or even which branes there are. But lots of U1s are going to disappear. I'm not sure that this is a complete list of mechanisms either. But to get a 5-10-10 coupling, we need to get rid of this particular U1. So we can reasonably hope to do that. But after we make it massive, the U1 will survive in perturbation theory as a global symmetry. See, this kind of mechanism, either one of these two, breaks the U1 as a gauge symmetry but leaves it as a global symmetry. Well, those global symmetries are not going to be exact because, in fact, there aren't any global symmetries, we think, in quantum gravity. And whether or not that's true is a general statement. There certainly are no continuous global symmetries in string theory. So there always is an instanton that will break the global symmetry. And therefore, if we've gotten rid of the U1, we can potentially get top quark masses, up quark masses. The only trouble is that if we get up quark masses from instantons, they're going to tend to be little. If this discussion makes any sense, and if something is coming from some kind of instanton due to a wrapped brane or something like that that breaks one of these global symmetries, it's going to be very little, exponentially small in whatever parameter justifies this. And even if you think that parameter is just 1/3 or 1 over 2 pi or something like that, it sure doesn't look like there's any suppression at all in the top quark mass. So a mechanism that relies on getting the top quark mass from a Ukala coupling that arose from an instanton effect doesn't sound promising. We have to make the instanton action vanish for the instanton that creates a top quark mass. The way to make an instanton action vanish, the instanton will typically be a wrapped brane of some kind, wrapped on some cycle. We have to collapse that cycle to 0 area or 0 volume. But when we do that, we're going to get a non-perturbative singularity. So if we want to get the top quark mass, we want an instanton of 0 action, and that corresponds to a non-perturbative singularity. That's actually one of the main reasons we need to do F-theory. We've gotten pretty far in this presentation without needing F-theory, just with D7 branes and O7 branes, O7 planes. And there's a lot more that I'll tell you in a moment that doesn't really require F-theory. But to get the up quark masses, we need a strong coupling singularity. Otherwise, the up quark masses will be exponentially small. And F-theory is the best way to understand that strong coupling singularity. So that's why we'll have to do F-theory. That's the main reason given by Beasley, Heckman, and Waffe. But I think I want to tell you another reason that it's good to use F-theory. Suppose you decided, well, I will describe the world in the approximation of ignoring up quark masses, whatever that means, for the top quark. I just won't bother with this strong coupling singularity, and I'll just use D7 branes and O7 planes. You would run into a topological problem, which you can solve, but you might not find solving it easier than learning F-theory. That's the only problem. The reason you'd have a topological problem is that so, as I told you, around the D7 brane, well, we have two things. A is a map from, I'm going to state this in a slightly more sophisticated way. We take space-time minus W. W is the world volume of the D7 brane. We take space-time and we remove W, and we regard A as a map from that thing to a circle. Instead of saying it's a real valued scalar field, whose periods, which is allowed to jump by 2 pi, we'll just say it's a map to a circle. And it's also supposed to have the following property. that if you take a circle that goes around W, so W is 8-dimensional and space-time is 10-dimensional, but I'll draw a normal slice. So this is the normal slice to W. And here's a point, P. P is a point in W. And here's a circle that goes around P. So in order to have a D7 brane, you need a solution of this topological problem. Space-time minus W, there should be a map from space-time minus W to a circle that has this property. Now, if you've learned if you've boned up on Bodin 2 and you're familiar with your topology, then you know that there's a topological obstruction to doing this. The topological obstruction is the following. The normal to W is a bundle of real two-planes, which has an Euler class, and the Euler class must vanish. Otherwise, this problem doesn't have a topological solution. Now, if you've never run into that problem, it's probably because when you've thought about branes, you assumed they were flat, or they had simple enough topology that you didn't run into this. So you ignored this, and it didn't bite. This isn't special to D7 branes. It has an analog for DP branes of all P. And if you run into a contradiction involving branes, if you've overlooked this, and you run into a contradiction involving branes, this could be the reason. I've seen it to happen. So, okay. Now, for the kind of S's that we want to use here, this topological obstruction is actually non-trivial. So it's impossible to wrap a D7 brane all by itself. Well, that's good, because if we wrap the D7 brane all by itself, we get U5 gauge theory without any matter, which isn't what we want to get. We want to get matter. And you see, this topological obstruction can be alleviated if there are additional singularities in the game. The additional singularities can come from D7 branes and Orientable 7 planes. So if you decided you don't care about the up quark mass, but you want to construct a model just from D7 branes and O7 planes, you at least would have to know what models actually exist. And you could start learning the kind of topology I'm telling you about. But an alternative would be to learn F-theory, which will generate the models that actually exist. It's a matter of taste. You could study Vafa's papers on F-theory, or you could read Bodin 2 and learn about the stuff I started to tell you about here. So if you find that avenue sufficiently distasteful, you might regard that as a second reason to learn F-theory. But seriously speaking, sorry. The fact that we'd run into complications this way, even if it isn't distasteful, and in fact, we can't avoid it. Often for D-branes, you'll find out that if you want to be careful, you need to understand this kind of phenomenon. But it's nice that this kind of thing is part of what F-theory will keep track of for you if you get familiar with those techniques. I shouldn't have said it quite as flippantly as I did. So I've told you why we need F-theory, but nevertheless, there's a lot we can do without F-theory still, and we're going to do some of that in the rest of the lecture. But I will stop just a moment again for questions.
Excuse me, we need Higgs or not in this kind of models?
In any kind of model, sorry?
Yes, so how
the Higgses are in 5 plus 5 bars of SU5. So in principle, I've told you where they come from. They come from intersections with an extra D7 brane. Yes?
Is there any way of distinguishing the Higgs 5-bar from
Well, there will be. See, I've been very vague so far. So I just said that C is a Riemann surface and there are some U1 fluxes. So to make the model work, I would need to tell you more about C and the U1 fluxes, which I'm heading toward. Now, Beasley, Ekman, and Vafa get a drastic simplification. they assume C can be contracted. Sorry. S. Unfortunately here it's C, but on the blackboard it's S. Can be contracted. That's what I told you at the very beginning. They get a drastic simplification because of assuming a local model where everything is happening in a piece of the manifold which they assume can be arbitrarily small. Now, they give a heuristic motivation for that. Okay. I might say that with or without the motivation I'm about to state, lots of physicists have been interested in doing that for the last 10, 15 years with all kinds of motivations. It's nice if the standard model doesn't depend on all the details of the compactification. But they make a specific motivation, which is to observe that the standard guts, SUSY guts, are asymptotically free, at least if you ignore the Ukala couplings. They're presumably not asymptotically free if you include the Ukala couplings. Are they? What? Well, it would be much nicer for what they say if they could be. Because if something lives, well, if something lives on a vanishing cycle, it can be decoupled from gravity. And if it can be decoupled from gravity, it should make sense by itself. And asymptotically free things make sense by themselves without any cutoff. That's the argument they try to make, and then they say that since the SUSY gut is asymptotically free, that motivates us to put it on a vanishing cycle. Now, like I say, it's a nice line of reasoning, but it bothers me because I don't think the SUSY guts really are asymptotically free when you allow for the Ukala couplings. It would really be nice if they could be, and if this suggestion they make would really make sense. Because of the Ukala couplings, I'm not sure what to make of their argument. But, at any rate, assuming S can be contracted leads to a drastic simplification, which I'll try to explain. Sorry, is there anything about asymptotic freedom that we should know? Okay. Well, you can report back later. Okay. Certainly, if you could make the SUSY gut model asymptotically free, it would make their picture nicer. But okay. Anyway, if we proceed with the picture anyway, assuming that C can be contracted is a drastic simplification because there are very few possible C's. There's a sense, and it's almost true that there's only one C that can be contracted. Although the way algebraic geometers would tell you is that there are 9 of them. Or maybe 10, sorry. Oh, darn. You're right, S. Right. There are only a few S's. So S is either, here's a complete list of S's. CP2, CP1 times CP1, or CP2 blown up at k points, where k is no bigger than 8. That's a complete list of the S's that can be contracted to points. Roughly the reason is the following. S has got to be a Kähler manifold of positive curvature. Well, okay. Let's remember Riemann surfaces. Okay. Sorry. I'm not sure how to intuitively explain that its Ricci curvature has to be positive to be able to contract it. But that's what? Okay, maybe that's right. All right, fine. So if you've contracted it, this is what Hermann is telling me. Right. I think it's a good idea, so I'll explain it. Suppose that S can be contracted arbitrarily much. Then we could go all the way and contract it to a point. And when we get it down to a point, we get a cone on S. And it's supposed to obey the Einstein equations. Well, in usual Calabi-Yalls, it should obey the Einstein equations with 0 curvature. In F-theory, maybe it needs to have positive curvature, slightly positive curvature. But anyway, that'll be unimportant near the singularity. So the cone, suppose we want a Ricci flat cone. Then it has to be a cone on something of positive curvature. For example, R6 is a cone on the 5 sphere. A cone means a metric that looks like this. Where, well, for a real cone, I've actually written it as if it's a real cone. Well, here we want a complex cone that's similar. But for a real cone, d omega squared would be a metric on a 5 manifold. And if you want ds squared to be Ricci flat, the most obvious way to do that is to take the 5 manifold to be a 5 sphere, and d omega squared should be the round metric on the 5 sphere, which has positive Ricci curvature. But in general, you'll find out that for this to be Ricci flat, d omega squared should have positive Ricci curvature. And here we actually want a sort of complex cone, but S should be a complex 4 manifold with positive Ricci curvature. And this is the complete list. CP2, for example, has positive Ricci curvature. CP2 has a standard metric, which is an Einstein metric with a positive cosmological constant. Every time you blow up a point, you make the integrated curvature a little bit less positive. And when you get past 8, it stops being positive. So there's this very short list of possible S's. And they have nice properties. But I decided I wanted to explain an example of what it means to contract one of these spaces. So I was going to do that for CP2, which is the simplest case. String theorists actually learned about it in reverse. This originally entered string theory by studying the C3 mod Z3 orbifold with 3 complex coordinates A1, A2, and A3, which you identify with themselves times a cube root of 1. That's a supersymmetric orbifold, which was one of the original examples of orbifolds. And if you study it, you find there's a twisted sector mode. There's a this twisted sector gives a Kähler modulus. By that I mean that the twisted sector gives a zero mode that has the right quantum numbers that would correspond to a Kähler modulus if you were on a smooth Calabi-Yau manifold. This is a singular Calabi-Yau manifold. And supersymmetry tells us that there's no superpotential with this amount of supersymmetry, so we can give a VEV to that scalar field. And since it's in a twisted sector, when we give it a VEV, we're not in an orbifold anymore. Giving that a VEV corresponds to turning the orbifold singularity to making this a smooth manifold. It's called blowing up the orbifold singularity, replacing the orbifold with a CP2. So if we give a VEV to this modulus, we blow up C3 mod Z3. And when you blow it up, you get a smooth manifold. And I want to describe the smooth manifold that you get. We take 4 complex variables, A1, A2, A3, and B. And we put a constraint. Well, we're going to do U1. This problem would arise in supersymmetric field theory if these are chiral superfields of charges 1, 1, 1, and minus 3 in U1 gauge theory. If we were doing that, then to find a vacuum, we'd have a D-term constraint. Which would tell us that A1 squared plus A2 squared plus A3 squared minus 3B squared is a constant, the Fayet-Iliopoulos coefficient, which I'll call little r. And would also tell us to divide by gauge transformations. And gauge transformations act by taking A1, A2, A3, and B to, well, the first 3 have charge 1. But the last one has charge minus 3. So to find the moduli space of Acura, we would obey the d-term constraint and also divide by U1. And of course, the moduli space of Acura in a supersymmetric theory is going to be a complex manifold. So this combined space is a complex manifold. Let's figure out what it is. First, we'll do it at r equals 0. Well, at r equals 0, so first of all, we use this thing here to make B positive. We could rotate B to the positive real axis by picking theta properly. And then we solve for B by saying that 3B squared is the sum of AI squared. So that determines B in terms of the A's. I gave you its magnitude, and it's on the positive real axis. But there were three ways to put B to the positive real axis. We can still get A1, A2, and A3 to multiply by a root of unity. Omega cubed is 1. That won't change the fact that B is on the positive real axis. So if R is 0, this space is just the orbifold. And it has a singularity when the A's are all 0. Now, suppose that instead R is positive. Then we find out that B squared is 1/3 of R plus the sum of AI squared. So minus R. So if B equals 0, which before was a single point, here if B was 0, the A's has will all be 0. Now if B is 0, we learn that the sum of AI squared is R. And we divide by U1. So we get CP2. So what used to be a single point when B was 0, and that was the singular point, is now a CP2 whose radius is the square root of R. See, A squared is R. The sum of A squared being R defines a sphere whose radius is the square root of R. And that's what I'm calling the radius of the CP2. So if R is large, we have a big CP2. If R is very small, we have a small CP2. And when R is 0, the CP2 collapses to a point. And when it collapses to a point, what we're left with is actually a cone. In this case, it's a very simple cone. Our cone is just the orbifold C3 over Z3, which is a very simple case of a cone where the metric is actually flat. It has a conical singularity at the origin. Now, what I've tried to show you is that it's possible to have a complex manifold that contains a CP2 of radius the square root of R, and that R is a Kähler modulus of the model, and there can be a limit when you approach a boundary of the Kähler moduli space when the CP2 collapses to a point. So the idea of getting GUT-like physics in a local description is that the whole GUT model is supported on such a vanishing cycle S. In my example, S is CP2, but as I've told you, there are 10 possibilities for what S could be. If we were really doing homework, I probably would have given a homework problem to describe for CP1 times CP1 in a similar explicit fashion how to make CP1 times CP1 collapse to a conical singularity by varying a Kähler metric. Maybe we'll do it this afternoon if somebody asks. So we've got this list of 10 manifolds that can each be collapsed to a point, and we pick one of them, and we wrap 5d7 branes, so we've got U5 gauge symmetry, and we use one of those tricks I told you about to get rid of the center, so the gauge group will be SU5. But we don't want SU5. We want SU3 times SU2 times U1. So the next step is to break SU5 to the standard model gauge group. And just like in the perturbative heterotic string, the only fields that can do this for us are the gauge fields on S, because they're this, from a four-dimensional point of view, they're scalar fields charged under SU5. So you might imitate the perturbative heterotic string and use Wilson lines. That might be the first thought, but the answer to that is no. Pi 1 of S is 0. There only are 10 S's, and they're all simply connected. Actually, as I talk to you, I'm slightly worried about something. There are more S's if you allow them to have singularities of certain kinds. Sorry. I don't think it affects this statement, though. So if we can't break SU5 with Wilson lines, what can we do? Well, there's something I've wanted to do for the heterotic string for more than 20 years, but it doesn't work. See, in the heterotic string, you could imagine turning on f of U1. You see, Wilson lines are very confining. They're fun at first, but you find out after a while that it's rather restrictive if that's the only way you can break SU5 in the heterotic string. So you'd like to break SU. It looks like you could break SU5 to SU3 times SU2 times U1 by turning on a U1 flux for hypercharge. In the heterotic string, that doesn't work. The reason no is that then U1 gets Higgsed. U1 hypercharge gets Higgsed. Here we're talking about U1 hypercharge. By a mechanism similar to what I was telling you about, to one of the things I told you about before. The kinetic energy of the B field of the heterotic string is something like this. And if we give a VEV to F, then the very same A that, so F is the curvature of some, so let's write it in more detail. It's a sum over a lot of fields of AI times Fi. I'm simplifying slightly, but it'll suffice to make the point. It's a sum over many fields of AI times Fi, and if we give one of these a VEV, the corresponding A is precisely the one that gets Higgsed. Now, the perturbative heterotic string could generate any number of U1s, and good riddance to most of them. But the U1 hypercharge is the one we don't want to get Higgsed. So we can't usually give a VEV to the U1 hypercharge. Of all the U1s of the heterotic string, that's the one that we can't give a VEV to, because if we did, it would get Higgsed. Now, there isn't really time today to explain why, so I'll have to postpone it till tomorrow's lecture or conceivably in the afternoon session. But in this F-theory story, there is no Wilson line, but instead you can give a VEV to the U1 hypercharge without it being Higgsed. So in the F-theory story, under what looks like it might be a mild restriction on B, we can turn on without U1y being Higgsed. I don't want to explain why that's true in this lecture, because we're running out of time and I don't want to rush through it. But unlike the perturbative heterotic string where you have to use Wilson lines, here you can turn on U1y without U1y being Higgsed if what looks like a mild condition is obeyed. Actually, there hasn't been enough study of the global geometry of these models to be sure that the condition is really as mild as it looks, but it looks like a mild condition. Now, okay, that's good because then you get the standard model, but there's a disaster waiting to happen. Well, first of all, before I tell you about the disaster, if all you care about is the symmetry breaking, there are lots of models because you could make many choices for the U1y VEV. But there's a disaster waiting to happen. So the adjoint of SU5 is 24 is equal to, under the standard model, the exponent is the U1 charge. Well, for now, I'm using a funny normalization of the U1 charge. What I've written in the first line is the adjoint representation of the standard model. And in the second line, I've written what are usually called the x and y gauge bosons of grand unification. They transform as 3,2 of SU3 times SU2, and they carry a U1 hypercharge, which I've unconventionally called charge 1. Well, we don't want any light x and y particles. That's clear. We don't want any massless x and y particles. And we're potentially in trouble because, okay, we won't get any massless x and y particles of spin 1 because we broke the gauge symmetry. But we are at risk of getting massless chiral superfields with the quantum numbers of x and y. The reason we're at risk is that we've got this complex manifold S, and we've turned on FU1, and we need to do index theory to find chiral superfields that transform like so. And we want there not to be any. And there's something nice that happens, which I won't tell you about. I'll state it now, but I won't explain it now. There's a unique choice of FU1 up to a diffeomorphism. In other words, up to a trivial equivalence, there's a unique choice of FU1 which avoids giving this kind of exotics. So there were 10 choices of S, and actually for CP2 there are no ways to do it, so only 9 models are left. And of the 9 models that remain, for each one, there's one good choice of FU1. So when we resume, I'll explain that, and maybe something else I just swept under the rug a second ago. Yes, why it is that U1y doesn't necessarily get Higgsed. And then we'll go on and have fun with some other things, and we'll even eventually have to do some F theory.